Okay, good. So welcome everyone. Thank you for joining this seminar today. I'm Giovanni Combello. I'm going to chair this session, and we are pleasure to have today Dr. Denis-Gabriel Caprace, and who's going to present about flow sensing for improved wake harvesting information flight. Just quick introduction. So Denis-Gabriel is currently a postdoc fellow at NASA Ames Research Center. He received his PhD degree in 2020 from UC University of Leuven in Belgium. And he also spent a couple of years at a flow lab at Brigham Young University before joining the NASA Ames Research Center. Dr. Denis-Gabriel research interest is in complex aeronautical system and their interaction with the environment, which I think is the topic of this talk somehow, and his research also are focused on looking for new solutions in the combined fields of aviation and sustainability. So that being said, just before leaving the floor to Denis-Gabriel, I would like to remind you that this session is being recorded and is kind of around 45 minutes. So there will be time for questions at the end of the session. So you can just turn on your microphone or write in the chat. So I think that's it. Denis-Gabriel, the floor is yours.
Yeah, thank you so much. Thanks for the introduction. And yeah, I really want to extend my thanks to the entire organization committee for giving me the opportunity to give this presentation. So today we're going to be talking about formation flight, and more specifically, we'll be looking into some flow sensing techniques that we have developed and improved in order to, let's say, enable and enhance a safe way of performing formation flight. So the topic of the presentation today, although I'm currently at NASA Ames, as you could very well hear, all the topic here is something that I started working on towards the end of my PhD when I was at UC Leuven. And I was really, I felt really lucky enough to be part of those investigations when they started. But then, you know how things go, you just graduate and you move on to something else. But you know, talented people took over, and I want to acknowledge the contribution here from Ignace and Victor. They've been able to take this way further, and so really a lot of the credit for the things that you're going to see in this presentation goes to them. So let me start with a very broad introduction, but I just want to point out how amazing nature can be, and how inspirational it can be for us as engineers when we try to come up with solutions. And I'll just want to, you know, point out a couple of facts here, like this little guy here, the bald-tailed godwit, is one of the birds we know travel the longest distance, and basically he is traveling across the entire Pacific Ocean on a single flight, let's say. So it's pretty amazing in terms of performance and flight performance. And you have other kind of birds that do similar journeys, very long distances, like certain types of terns, and then swallows who can fly for an extended period of time, and we're talking about months without ever landing. So all those things that, you know, when you look at that, it's really just amazing and mind-blowing how that can happen, and it's a great source of inspiration. Now, one of the consistent behaviors that we observe with birds is formation flight. And here we're talking about this kind of organized way of flying where the birds fly in these V-shaped formations. And that's been always kind of a source of wonder. So why they do that? And there's been many theories involved, but one of the theories that prevailed eventually was that they are getting an aerodynamic benefit by flying in this V-shaped formation. So we're going to look into that, but that's one of the the things we think motivate formation flight for birds. So it's been, of course, the topic of studies for a long time, and first of all, theoretical studies. I'm putting a list here, a very short list, but just to for giving you an idea of the dates that we're talking about. So early studies, beginning of the last century, but it's not until the 80s that we really get an idea of how much those birds can save energy when they're involved in formation flight. So here I'm borrowing this figure from Hummel in 1983. And what he did is using very, let's say, conventional aerodynamic tools, textbooks, theories, and also using many assumptions, like the study here, it considers steady wings, so it's not even considering flapping flight or whatever. But he was able to come up with this measure of how much power the birds save when they're in formation. And that is as a function of the lateral spacing between the birds. So here 0 would be 2 birds flying kind of tip to tip. So really there's no lateral distance between the birds, and you can go negative if there is some overlap between the tips. He also studied the influence of the size of the flock, but let's just look at 2 birds. One thing to keep in mind for the rest of this presentation is the order of magnitude that we're looking at. So we're talking about saving on the order of 10 to 20% of power by just flying at the right position in the wake. So it's kind of a big number, but that's what we're talking about here. And to understand really where this power benefit comes from, it's way easier to look at a steady wing that flies, at a certain velocity, and just because of Newton's third law, what you will have eventually is that you have wake vortices that develop behind the wing, and that's of course something that you can visualize quite easily on an airplane which has contrails here. And what those vortices do is that they will induce a velocity on their surrounding with an upwash component outboard of the vortices and a downwash component inboard of the vortices. Now, what formation flight is about is really just flying into this region where you have upwash, and you can see that you have higher upwash velocity closer to the vortices. And you can surf that region and getting benefits out of those upwash velocities. And what happens is if you fly in this upwash, if you consider first an isolated airplane that travels at a certain velocity, so you have a relative velocity to the air, and of course you can decompose then the forces on the wing in a lift and drag. But then if you have an upwash velocity, you're changing a little bit that relative velocity, and the result is that you're tilting this system here, and basically the lift vector is tilted forward. Excuse me. So if you compare the two cases here, the lift, when you fly in an upwash, the lift is tilted forward, and there is a slight thrust component to it. And that's all about formation flight. It's actually maybe not producing thrust, but actually reducing induced drag through the presence of upwash velocity. So we know about the theory and how much theoretically it could be saved, but then you can also say as well, let's just go in flight and let's just verify that number and see how much we can save with actual airplanes. And that's been the topic of numerous flight test campaigns, starting in the 90s, again with Hummel. He wanted to verify the number that he got with theory, and you can see he obtained like 10% of savings during this experiment. So it's pretty close to what he was expecting. Then NASA has been doing also several experiments, starting with fighter jet here, and you can see they reach pretty high value of savings. And that's because they're really going into that region where you have overlap between the tip of the wings, as you can see here. And so that's what gets you to very high saving values. Another, in my opinion, quite interesting study was a more recent one where they used these business jets. And one of the focus there was to try to understand how turbulence affects the smoothness of the ride, meaning that you don't want for passengers of the airplane at the back for the flight to be too bumpy. And so they highlighted that even though, of course, you can reach 10%, you might have to tune that down a little bit if you want to make sure that the level of turbulence is still acceptable. And so other studies, always kind of in the ballpark of 10% saving, and more recently also by major aircraft manufacturers, which just demonstrates the momentum that is currently building up around formation flight. So it's pretty good to see. And it's also pretty understandable when you consider, first of all, the state of air traffic today, and in perspective with the current climate crisis, of course. So we're talking about 10% savings in drag, but that would also be like fuel savings and emissions that you're saving. So and when you look at certain regions of the airspace, like over the Atlantic Oceans, you have those all those airplanes traveling roughly in the same direction, and it's pretty obvious to imagine a way. I wouldn't say obvious, but you imagine that it could be done to group those airplanes in such a way that they can perform formation flight and get those benefits. Yeah, but so that's what we're looking for, but then there are still challenges that need to be overcome here if we want to be able to really fly airplanes in formation. And the biggest one, of course, is safety. You want to maintain and make sure that both airplanes are safe at all times during formation flight. So with that in mind, one of the first things you realize is that you're not going to be allowed to fly those airplanes in what we call close formation flight, meaning that you have one airplane and right behind it, or a couple of wingspans behind the first airplane, you have the second airplane, because the risk of collision is just too high. So what's going to more likely happen is that you're going to fly what we call extended formation flight, which is it involves a streamwise distance between the airplanes on the order of 50 wingspans. So we're talking about a couple of miles in spacing. Now, at those distances, what happens is that you actually need to have a better idea where the vortices are located. And that's for two reasons. First of all, so of course, they're not visible at all times with contrails. So there can be situations with no contrails. So you want to know where the vortex is because you want to maximize your benefits with respect to formation flight. So, and for that, we've seen that you have to be located quite close to the vortex, but also you want to avoid at all costs to encounter the wake vortex, meaning flying through the vortex, because that could result in a loss of control for the airplane at the back. So that's really the challenge that we focused on in this work, and trying to come up with a way to determine what's the position of the vortices in order to fly safely around them. And so there's a list of other challenges here, but really we focus on wake sensing and vortex, locating the vortices here. So what I want to do in this presentation is going over a couple of the tools that we developed to in order to do that wake sensing, and then we'll go over some results. I'll try to show you how the filter performs and what are advantages and maybe limitations of those filters that we develop, and then I'll circle back to the aerodynamics of birds, because I want to compare that to what we have seen for airplanes. So let's start with the tools and modeling capabilities that we developed. So just to make it clear, yeah, what we're trying to do here is determine the relative position between the follower airplane and the leader of the position of the wake of the leader. So I'm going to be talking about the leader when I refer to the airplane in the front, and the follower is the airplane at the back. And you can see there is this quite long distance between these two airplanes. And so we're looking into those two quantities here. And the thing is, there can be some factors that will influence the motion and the position of the vortices when we're talking about long distances like those. And those factors can be like turbulence, but also interaction between the turbulence and the vortices, which can then develop fundamental instabilities, and that will affect the position of the vortices over time. So that leads to a certain uncertainty and that's why we think estimation can be a solution to better mitigate that uncertainty. So ideally, that's what we call wake sensing, so the determination of those quantities. And ideally, we'd like to do that without any communication between the airplanes. And that is just because if you want to implement formation flight as soon as possible, you'd like to limit the number of additional systems that you need on the airplane to perform formation flight. But then when you know the relative distance between you and the wake, you as the follower, well, you can imagine that you can turn on what we call the tracking. And that means using your autopilot to fly constantly at the, let's say, optimal position in the wake that gets you those maximum benefits that you expect from the wake vortices. And so we're going to talk about sensing when we try to determine the position of the vortices, and then tracking when we actually fly using those estimates in order to maximize the benefits of formation flight. So we're trying to sense the wake. So then the question is, what sensors do you need for that? One thing you can think of kind of straight away is using relative position. And so that works pretty well when the airplanes are in close formation flight, so they're close apart from each other. But then because of that uncertainty in the propagation of the wake that I was talking about, it lends itself a little bit worse for the extended formation flight. So that's something that we will not consider in this work. And then another idea you can have is, well, let's just measure the vortices directly. And that's something that you can do through LiDARs, for instance. So there's been works in the literature with that. But again, that requires an additional system. And if you want to install that on an airplane, you will get into certifications and things like that. So it's going to probably take some time before airplanes are equipped with that system and you can actually fly formations. So for that reason, we're not looking into that. Instead, what we're going to be seeing in this work is the last two options here. So this one, the third one, is still using an additional system, but maybe a little less, how I can say that, takes less volume from the plane, let's say it like that. And so that would be using some sort of distributed measurements across the wing. So instead of sampling an entire 2D section of the flow, you can just have a couple of probes that will give you an idea of what's the state of the flow around you, and then from there you can imagine how to determine the position of the vortices. And that idea has been used previously in the literature in similar studies. So we'll look into this one, and the last one is the one that we thought would be more promising in the context of formation flight for an application as soon as possible, and that would be using only measurements that you already have available on board an airplane. And when you think of it, what you have already is everything related to guidance and navigation. So position, velocity, attitude, control surface deflections, all those quantities that the flight computer already needs to actually guide the airplane. And so what if we can use those measurements in order to determine the position of the vortices? And so that's one of the questions that we had and that we'll investigate here. So we'll need an environment, simulation environment to perform those investigations here. So let me just go over the main pieces that we need. So we'll have a high fidelity CFD solver, which is kind of one of the main building blocks of this environment. And that's because we want to capture the physics of those wakes. And as I was mentioning, you can have interactions between turbulence and the vortices. And so we really need, we really wanted to have that kind of fidelity in order to make sure that the propagation of the wake is accurate, and you can have turbulence as a source of perturbation and noise in the estimation. Now, the CFD is coupled to aircraft models. Those are 6 degrees of freedom models, and so basically just allows us to integrate the position of the airplanes as a function of time. And from those bricks here, we take measurements. And so the whole idea of the estimation strategy that we put together is taking measurements out of those two, putting that and feeding that into an estimator that we still have to determine and define, and then you hope that out of that estimator you can get the position of the vortices and their strength. So that's about sensing, and then when you do tracking, as I was saying, you can feed that back into an autopilot that will control the airplane and make sure that the follower stays constantly in a right spot. So let me just go over each of those models with a little bit more details. So we have the high fidelity wake solver here. It's based on the vortex particle mesh method, but that's not really important. What I just really want to emphasize here is that we capture those little instabilities and the natural way the wake is influenced by the turbulence. So I don't know, you can probably not really see it, but there is some blue background light here, which is actually the turbulence. And what you can better see is how the turbulence affects the position of those vortices when they advect downstream. And that's why they kind of wander a bit. So we captured that in the simulation. Then you have the aircraft model. It's again a 6 degrees of freedom model, meaning that we can have the full dynamics of the airplane. We have control surfaces, an autopilot, and all that is integrated into the high fidelity CFD solver. And now comes the cornerstone of this estimation, which is actually the estimator. So before I go into this, I'd like to mention that there are several ways of attaining that goal of determining the position of the vortices, or at least find the right spot in the wake where you want to be in order to maximize the benefits. And another thing you can think of is deep learning. You could teach an aircraft how to fly into a wake. That's something that I will not talk about today, but I have a couple of backup slides if someone is interested. The advantage here of the estimation based on estimation theory and Kalman filters basically is that you will estimate the position of the vortices, but you will also have a degree of confidence in that estimate. And we think that is really an advantage with respect to safety. So the way it works is as follows. So just a refresher on let's say, Kalman filters in general. So you have an actual system that you can take measurements out of. So those measurements are these, the Z vector here. So they come from an actual airplane, or in this case, they come from the CFD and the high fidelity aircraft model. And so they come into the Kalman filter where I have a state vector and a state representation of the system through a surrogate model. So the surrogate model is located in here. It's actually those function f and h. And what it allows to do is, if I have the state of my system at a certain time, I can propagate the state through the surrogate model in order to guess what's going to be the next state through time. So I'm getting a prediction for the next state of the system, and then also a prediction for the measurements. Now I can compare the predicted measurements with the actual measurements that I'm getting from the actual system. And I can, the difference of that can inform the knowledge I have of the predicted state in order to provide a corrected state, which would be that Qn+1. So it's always like that. You have like this propagation step and then correction or analysis step that incorporates the knowledge you have of the system into your predicted states. Now, there is also here an additional step involved, and that's because we're using the Ensemble Kalman filter. So Ensemble here means that we're basically using a Monte Carlo approach to obtain the statistics that we need in those steps. And I don't want to go into the details here, but I can, of course, if anybody has questions. But the idea is that we use that approach because it's much more robust to nonlinear systems, and that's what we have here. So that was a real motivation for going for that type of filter compared to other more conventional filters like a Kalman filter or an extended Kalman filter, let's say. So now we know about the estimator. What we still need to determine is what we put in this box. So what's going to be the surrogate model that we use. And the surrogate model should rather be something quite simple and also computationally efficient, because if you want to do real-time sensing, you need to be able to propagate that model often, let's say often in a real configuration. So this model here is based on the Prandtl lifting line for the aerodynamics. So we have a couple of lines that represent wings, and they are influenced by two infinite vortices, actually regularized point vortices, but so those vortices have an induced velocity similar to the actual wake. And so they influence the aerodynamics of the Prandtl lifting lines. And then on top of that, we still have our dynamics. So the 6th degree of freedom dynamics of the airplane that we can integrate, and the autopilot. So that's the surrogate model. And I can skip that probably. I just want to summarize here the entire strategy. So we start with the actual system, which is what I presented in the beginning. So it has the CFD simulation. It has the aircraft dynamics through the 6 degree of freedom model and the autopilot. So that is what we hope we could swap with actual airplanes flying in reality. But in this context here, we take measurements out of that. We input that in the Ensemble Kalman filter. The Ensemble Kalman filter has this surrogate model in there, and it performed the estimation so that in the end we have an estimate for the position of the vortices, the relative position, and their strength. And then eventually, as I was saying, when you do tracking, you can feed that back into the system and provide that information to autopilots in order to follow the wake vortices. Okay, that's it for the modeling. And now what I want to do is show some results. And we'll do it kind of gradually. I'll start with very simple configurations and simple systems. And then I'll add more complexity towards the end. So in this section, you're going to see a lot of charts that look like this one. So let me just walk you through how to read the information here. So we're looking here on the left at the 2D cross-section of the flow located at the position of the follower airplane. So you have this black line here, which is the wing of the follower. And then you have a representation of the tip vortices that we're trying to locate. So these are the two blue dots. And on the left-hand side here, it's everything related to the current state of the filter. So you have the current guess for the position of the vortices, which is materialized with the two crosses here. You have the history of the estimated position. And then the red area is that confidence interval that the Kalman filter provides. And so basically, the smaller that region is, the more confident you are in the estimation that you're currently doing. So let's start with something very simple. We're going to look at an airplane, a follower airplane that actually has no dynamics. So I turned off the autopilot, turned off the dynamics. I'm just fixing the position of that airplane in space. It's located right next to the vortices that it's trying to locate. And I'm using for this one, remember those distributed measurements across the wing, which give me a sense of the state of the flow around me. And that's the only measurement I'm using here. And so if I turn it on, you can see that the filter actually works. It converges to the position of the vortices, which is great. Now, that's not really new. That has been shown in the literature before that it can work. Now, what's novel here is the use of the Ensemble Kalman filter. And I was talking about nonlinearity and robustness. What happens is that I can put my initial guess for the system pretty much anywhere in that 2D space, and the solution will converge to the actual solution. And that was not the case, for example, in previous studies that used different types of filters. Now, I can do something a little more complex and try to estimate the position of those vortices when there is a vertical offset between the follower wing and the vortices. And you can see here then that you run into an issue, which is there is some kind of symmetry in the system that does not allow you to discriminate whatever happens on the above, let's say, half plane of the follower airplane and what happens under, meaning that basically the influence of those vortices is the same no matter if they're located under or above the wing. And that's just because of the nature of those measurements that we're taking. So that's going to cause an issue here. And so we can try and solve that issue. One idea that there was in the literature is that if you add unsteadiness in the signal that you're trying to estimate, you're improving observability. And that's actually the case here because the filter converges pretty fast to a solution, but still here, because of that symmetry, you're not able to guarantee that the solution converges to the actual solution that you look for. Another idea that we had here is that if you add dynamics now on the follower airplane, you might also help the estimation. And that is because if, let's say I am converging to the wrong solution, then if the follower moves a little bit, it will get closer to one solution and further away from the other solution. And at some point, the filter will realize something is wrong and it will switch to the actual solution. And that's exactly what just happened here, if you paid attention. So by moving the follower a little bit, I was able to converge to the actual solution. So there is this idea that the dynamics of the follower airplane itself can help in improving the quality of the estimation. Now, unfortunately, there's no free lunch. And if you really want to make sure that you get rid of that symmetry issue I was mentioning, you will have to add a new measurement. And so just to make it clear, what happened here was that if you have vortices located somewhere in space, so they will have an influence on the main wing of the follower, but that influence is going to be the same no matter if it's located above or under the plane at the same distance from the symmetry plane. Now, if I add another measurement, let's say using something that happens with the vertical tailplane, and that could be a yawing moment, for example, or the deflection of the rudder, or so something that has to do with the lateral dynamics of the airplane, then what I'm getting is a different configuration in each quadrant of the space here. So that now means that if I add this measurement, I should be able to discriminate those solutions and make sure that I'm getting the right solution. And so if you do that, actually, yes, it works. And you can see that the estimation gets to the right solution and gets locked onto it. And what happens here is that I turned on both a simplified dynamics of the follower. So you can see that the follower wing responds to the presence of the vortices, which helps the estimation. But also I have this additional yaw measurement that I'm using to discriminate between the solutions, and then I'm getting a correct estimate over time. So those were relatively simple cases, but then, and they were all using those additional sensors distributed over the wing. But then the big question I told you we had is, can we use only the dynamics of the airplane, meaning only measurements that you already take on the airplane in order to perform the estimation? And that's what we're using on this slide here. So it's actually a jump in complexity, not only because we're using those dynamics measurements, measurements from the dynamics, so the position, velocity, also angle of attack, side slip, and the control surface deflections. But in this case, the dynamics of the airplane, of the follower airplane, is of course turned on because I want to take measurements out of it. But so we also have the autopilot, which for this case controls the airplane so that it flies in a straight line. So that's why you can almost not see it moving here. And the flickering at the back, if you can see it, is actually the turbulence that we have in the simulation. And so that's a natural source of noise for the entire estimation process, because it generates those instabilities that we saw in the wake of the leader. And but so if you followed me, basically what happens here is that the estimation still works, even though it's based only on those dynamics measurements. So we kind of demonstrated that this approach can be utilized, and we managed to get to a correct estimate with a certain degree of confidence, which is, again, something that we look for regarding safety. We want to have an estimate of the position of the vortices, but also now how confident we are about that estimate. Now that was sensing, and the last thing I can do is turn on the tracking. So if I have vortices that are moving, then I can instruct the plane to follow those vortices and use the autopilot for that. And that's what this little video is showing. And actually, in this case, it also helps the filter because, again, you have dynamics going on with the follower, which improves the observability, and also you stay closer to the vortices at all time, which again helps you in having a higher confidence in the estimate at all times. So let me now share some of the lessons we learned in this entire process, and that was, let's say, a learning process for us at least. So there was this ambiguity in the position of the vortices, and due to that symmetry that I was mentioning before, there's another kind of symmetry, if you like, in the system, which I didn't mention so far, but it's this idea that if you have a, let's say, a strong wake that is located far away from the follower, it actually has a very similar influence on the follower as a weaker wake that would be closer. And so you have that trade between the lateral position of the wake with respect to the follower aircraft and the circulation of the wake vortices. And that's what this that's what this figure is showing here, that if you're not paying attention and if you're not providing any information about the circulation to the filter, it can get a wrong solution where, for instance, here you would have a too high estimate of the circulation at the too far position. Whereas if you provide some information about the circulation, then you can get to the right solution. So that means that practically, if you want to implement this solution in actual airplanes, you would need some sort of way to determine what this circulation can be. And that could either be through a communication between airplanes, so you would still need that actually, or maybe just a gross estimation or an educated guess, I would say, of the mass of the airplane by just looking up its type, for example, might be enough to have that little information we're missing in order to make sure the estimation does the right thing. And the last item here that I want to mention, which is kind of one of the limitations of the filter, is that the surrogate model that we use inside the Kelvin filter needs to be relatively accurate in reproducing the natural dynamics of the follower airplane. And that is because, when we use only the dynamics as measurements, what the filter is actually doing is it's discriminating between what is the natural dynamics of the airplane without influence of the vortices, and what part of the observed dynamics is due to the wake vortices. So if you have, let's say, biases and noise in the surrogate model, then the filter might not be able to identify what is the influence of the vortices. So that's all about wake sensing and tracking, actually. Let me now, I'd like to very briefly conclude by showing you those wakes of birds. And so the question you can ask after seeing all this for airplane is, so birds have been doing that for forever, basically, and how they do it. I mean, do they need that kind of sensing? And so how are they able to fly information? And so the first thing to realize is that, well, the wake of a bird is slightly different from the wake of an airplane, in that you're going to have vortices, but they're not going to be straight vortices as in the case of the airplane. And instead, what you're going to get is some oscillations and variation in circulation, depending on the position, because the bird is flapping. there was also a theory that depending on the gait of the bird, so how the wings are flapping, you can have a wake made of vortex rings or something more continuous. So the idea here is that we can use that CFD simulation tool that I mentioned to study that and perform simulation of a bird and try to see what the wake looks like. And that's actually the work of my colleague Victor for his thesis, and he got to this solution, which is a simulation of a bird. There's actually a lot that goes into this because the aerodynamics is through the CFD tool that I presented, but then there is an actually quite complex biomechanical model of the bird that includes the bones, the muscles, tendons, and all that kind of stuff, and also something interesting here is that the bird is actually in trimmed condition, let's say, on average, so meaning that the lift equals the weight and the thrust equal the drag on average. And so there was a lot of effort going into controlling that bird and stabilizing it in the simulation. But then, I have references about the models involved, and I can show that in the end. But then when you have that wake, then you can compare it to what you know from airplanes, and you can see that there are regions of the wake that look like what you expect with, let's say, strong tip vortices, and they actually correspond to the moments when the bird was producing most of its lift. But there are also other regions that look a little different. Now, the good thing about this simulation is we believe it's physically correct in the sense that all the vorticity field is still solenoidal, and so all the loops in vorticity are closed. And now we can use this wake for more investigations. And one of them can be formation flight. And I just want to show you this one, which is interesting in the sense that now you have two birds. The bird at the back is again flying in trimmed conditions, so is at equilibrium, let's say, and you can see that it's flapping its wings in phase, meaning that if you look at the tip of its wing, the tip is actually following the path of the tip vortex of the bird in the front, and that has been shown to actually happen in nature. So some species of birds, they know that doing so and adapting their flapping frequency and flapping phase to the vortices that they have coming out of the leader will maximize the benefits, the aerodynamics benefits. So they have to have a way of sensing the wake in order to adapt. But what I want to point out here is in terms of sensing, this configuration here has all the factors that I mentioned were beneficial for the sensing. So we have a lot of unsteadiness and three-dimensionality in the wake of the leader, which has been shown to improve the observability of the wake, and also the bird, so the follower bird has its own dynamics, and so those two factors may help in sensing. And also they're flying close formation, so they can most likely use their vision to position themselves. And the very last slide I have here is just about now that you have this model, you can basically do exactly the same mapping as the one I was presenting here from this theoretical study in the introduction. And so you can, now that you have flapping and the complex wakes and all the models that are involved, you can have a similar estimation of the power that you gain from formation flight. And what I just want to point out here is look at how close the values are from the theory. That's really something that is mind-blowing to me. It's like, even though you have a lot of complexity. The simple model was pretty close to the solution that we're getting here. Now, of course, we also have unsteadiness. We also have assumptions in those simulations, but this is still good to have a look at. So if you're interested in those results, I invite you to look into publications. This one is not published work yet, but look up for the work from Victor and follow him on ResearchGate, or if you want to get updates, but look for that. And I'll just finish with a brief conclusion. So we've performed wake sensing using different types of measurements. We've been able to show that the unsteadiness in the wake and the dynamics of the follower are factors that help in increasing observability, but also we need to be careful about what measurements we use. And we demonstrated that the use of the follower dynamics can be sufficient to perform wake sensing for formation flight, as long as you have an accurate model for the dynamics of the follower airplane. And then in terms of the benefits of formation flight, we didn't bring any new elements here. So I think realistically, we're talking about 5 to 10% drag reduction for the follower airplane in formation. Something that we brought in this study, though, is this capability of providing a confident estimate of the position of the vortices, which is something you need when you want to be able to safely fly in proximity of those wakes. And with that, I just want to acknowledge funding sources, computational resources, also Professor Jeff Eldridge, who was involved in the beginning of this project. Here's a list of references. I can probably put that in an email if anybody is interested. And yeah, that's all I wanted to say. Thank you very much for your attention, and I'm happy to take any questions.
Well, thank you, Denis-Gabriel. It was, at least on my side, amazing talk. A lot of very interesting things. So I guess there are questions. At least I have a couple of questions, but if anyone has any question, just write down in the chat, or better perhaps turning on the microphone and asking the question. So anyone that want to ask something, I might start, just breaking the ice. Just out of my curiosity, so how many pressure sensor have you used when performing, the first?
Yeah.
It was like distributed or?
Yeah, distributed. I think there was not much. It's probably nine sensors in the beginning. I don't remember doing any sensitivity study as to how many or what's the minimum number you need. Theoretically, 2 would be sufficient, but I took 9 just because it was a little more, and yeah, there was no real justification for it. But
okay, I don't see any comment in the chat or anyone raising a hand to ask questions. So I'll have another one. So how really real time is this estimation? I mean, I think there's always some delay between measurement and say estimation. So
yes, absolutely. Yeah, I can talk a bit about that. So the what we're doing now is not real time, because first of all, we're using that high fidelity CFD, which of course has a time step that takes much longer than real time, right? That's not an issue for us. But then if you think about actual application of it, I agree. So there are delays in sensors and also actuation. So what we studied was the influence of having let's say a cutoff frequency in the actuators. So making sure that basically you're not actuating the airplane at a frequency that is higher than the response of the actuators. Okay. Now, the delays of the system we haven't been looking much into that because I think the fundamental frequencies of the vortices might be actually slower than what we expect would be the frequency of the electronics and sensors. But this is an this is an idea we have, and we haven't really checked. It's just, you know, out of our understanding of how those things work. But that could be, there might be situations where the vortices change very fast in time, and then you will obviously have delays in the the ability of the filter to respond to those changes. Yeah.
And we have a couple of questions from our participant. To Jorn, raise your hand. Yeah, go ahead. We cannot hear you.
Can you hear me now? Is this working?
Very low.
Oh, how about now?
Yeah, it's
perfect.
Okay, yeah, I had the wrong mic. Apologies. So I thought it was really cool how you were able to sort of minimize the amount of information, but you were still able to deal with sort of turbulence. It was quite impressive. I guess, yeah, I didn't expect that at all. What about the opposite? What do you think, how would you, if you want to do the opposite, if we had just a bunch of really terrible, cheap sensors, lots of uncertainty, what would you choose? And do you think that's even a viable solution worth pursuing?
Yeah, it's a very good point. I think it has to do with the limitation I was mentioning. And for systems where the noise and also your knowledge of the system is quite poor, I think the solution I presented based on dynamics only, or a limited number of sensors, might not be viable, because you really need that ability to discriminate between what is from the system and what comes from noise that is measurement noise or whatever. So if you have, if you can have a lot of those, let's say, cheap sensors, then I would rely for something like more like what I showed in the beginning, and with those pressure sensors or whatever sensors that can really inform about the flow directly, whereas the other solution, it kind of senses the flow, yes, but through the dynamics of another system. So if you don't know the dynamics of that system, then that doesn't really work.
Cheers, thank you.
Gaetan, yeah.
Yep. Hi, thanks for the very nice talk. Can you hear me?
Yeah.
Yes.
Yep. Okay, so I understand the interest with working with a limited number of sensors to increase the robustness, in the sense that you don't need to get that much information. But in real condition, if you also have the position of the leader plane, you would use it. But if at some point you lose that connection, is this kind of filters or Kalman filters or other control techniques capable of dynamically removing some information, or on the contrary, adding on top of, like in real time, adding new information and incorporating them into the system?
Yeah, that's a good point. So my understanding would be that if you use a sensor and then you lose information at some point, because you lose communication, for instance, as you mentioned, you can still perform estimation using like the last best measurement that you had. And in this case, let's say, for example, that you rely on that communication to have that additional information about the strength of the vortices that are coming. So let's say you were exchanging, for example, the weight of the airplanes through a communication. If you lose that link, it's not a big of a deal, because that weight is not going to change by very much over time, so shouldn't be an issue. Now, if you're telling me that at some point you lose half of your pressure sensor that you were using for the estimation, then I don't give a lot of confidence in whatever estimation comes out of the estimator after. Now, adding measurements in real time, we didn't consider that. I guess it depends on the type of measurements that you're thinking of, but the way, at least the way we implemented the filter and the surrogate model, it's kind of the same thing. You would have to have an initial guess for the measurements that you don't have in the beginning, and then at some point during the estimation, they turned on, and then the filter adapts. But I don't see any easy way to add unexpected information, let's say, because you still have to have your surrogate model that is designed to handle the information. That's what I mean.
Thank you.
Thank you very much. I think there is one question in the chat, but perhaps this is something that you can address perhaps in private via email, just asking about that deep learning method instead of the Kalman filter. So unfortunately, we are been running late a bit. So perhaps, yeah, Kundan, if you're really interested in that, perhaps you can have a chat or via email.
Sure. Let me just, we have a publication on that. So
yeah,
let me just pull that out. And of course, I'm happy to have a separate discussion with whoever is interested. Let me just try to go here. So you can look up which one is it? I think it's going to be this one. So it's an AIAA paper, SciTech 2021. So it's still kind of a preliminary work, but it shows how at least one way of doing the estimation using deep learning.
Thank you very much. Yeah. So I think we can conclude this very, very interesting talk. I guess with some very interesting follow-ups. So we thank again Denis-Gabriel, and thank you for attending this seminar. So I'd like to invite you to the next one next week. So we thank again Denis-Gabriel, and thank you everyone, and enjoy the rest of your day.
Thank you very much, and thank you for having me.
Bye.